All right, so we're going to go through the questions in your homework tonight, just to make sure everybody's comfortable and okay with those. All right, so we've got a block of metal, which has mass 10 kilograms, is dropped from a height of 40 meters. How much energy does the block have before it is dropped? So hopefully you're recognizing that in this Q1 here, the first thing is that since we're dropping a block from a height of 40 meters, it starts with gravitational potential energy, right? So that is our energy potential, and that for gravitational potential energy is equal to mgh. All right, so since we're starting with that, we can go ahead and put the mass in, which was 10 kilograms, g, which is 9.8 on the surface of Earth, and the height, which is 40, and we should then be able to calculate the gravitational potential energy. So 10 times 9.8 times 40, and we get our answer of 3,920 joules. So that's how much energy it has before. Now, in the second part, the question says, how much thermal energy do the block and floor gain when it hits the floor? Well, we're assuming that it's starting with this gravitational potential energy, that as it falls, that gravitational potential energy is turning into kinetic energy, right? And that as it hits the floor, all of that kinetic energy is going to be taken away. Now, where does that kinetic energy go? Well, if we're assuming that the floor stays stationary, eventually the block will come to rest on the floor. Energy can't disappear. It's got to go somewhere. So if we assume that both the block and the floor are at rest at the end, that means we don't have any potential energy, we don't have any kinetic energy. All of the energy must have gone into sound and heat. All right, now for this question, they're just asking us how much thermal energy do the block and floor gain. I would debate that, well, actually some of that energy probably went into sound, but if we make the assumption that it all gets turned into thermal energy, then we would say, well, it started with 3,920 joules of energy at the beginning. All of that is going to be turned into thermal energy. And so the thermal energy, assuming that energy is conserved, is 3,290 joules. And that's what they're trying to get at here. Just the idea that we are conserving energy. All right? Let's go ahead and look at the next one. The next one says, if the car in the second worked example on page 158, so that's the previous page, okay, what we know about that car in page 138 is that it has a mass of 1,000 kilograms. So here we go. It says it is traveling at 60 meters per second. So that's my initial velocity. How much thermal energy would the brakes receive? So this is assuming that it's starting at that and then it ends at 0 meters per second. So we apply the brakes, the car stops. How much thermal energy would the brakes receive? This is assuming, again, that the tires do not slide. If the tires slide, then some of that energy is going to go to heat with the ground. But if we assume that there's no sliding, that none of the energy goes into the ground, then all of the energy that we start with must end up as thermal energy in the brakes, between the brake pads and the wheels that they heat up, right? So in this case, we know that we're starting with some velocity, so we're starting with kinetic energy, which is equal to 1/2 mv squared. And so we just go 1/2 times 1,000, because that was given in that question on the previous page, times the velocity, which was 60 squared. And we go ahead and plug that in, 0.5 times 1,000 times 60 squared. Oh, just kidding. I need to put 60 squared. And I get 1,800,000, which is 1.8 megajoules. All right, so that's how much it starts with. Obviously, at the end, if the velocity is 0, then all of that energy has to be converted into thermal energy. And so, therefore, the thermal energy in the end must be equal to 1.8 megajoules. That's how much energy it would take to slow the car down, take out all that energy, and all of that would be turned into the heat in the pads. Now, as a kind of interesting side note, this is essentially how hybrids work. Hybrids have a way of taking that heat, that energy, and using that to recharge a battery, right? And so when you use your car and you're using your brakes, a hybrid will take this energy. Obviously, it's not 100% efficient, but it will take this thermal energy and it will convert it back into electrical energy, charge up your battery, and then, of course, you can use your battery as you're driving around. So kind of an interesting idea. I believe most electrical cars will do that as well, is that anytime you're using the brakes, they will try to do something with all of this heat energy that's being lost. So kind of a cool idea, cool principle. Obviously, we don't have the science necessary that we could do that, but the idea that that could be done is interesting. All right, let's move on to number 3. All right, number 3 says a 75 kilogram free fall parachutist falls at a constant speed of 50 meters per second squared. Calculate the amount of energy given to the surroundings per second. All right, so this is a little bit different, right? So we're starting that we have a mass of 75 kilograms that has a constant velocity of 50 meters per second. And the question is, how much energy is given to the surroundings per second? So that's power, right? That would be energy per time. Now, if you look at it at first glance, you say, well, if the velocity is staying constant at 50, that means that my kinetic energy is not changing, right? So what is this? Why is energy going to the surroundings? Well, it's a parachutist, right? They're falling. And so if they are falling, then that means they are losing gravitational potential energy. Now, that gravitational potential energy normally, like in our first question, would be converted to kinetic energy. But if there's enough resistance that the parachuter stays at a constant velocity, that means the energy must be going somewhere else. It's got to be going to drag. It's got to be going to thermal energy. So that's why it's saying that energy must be going to the surroundings. So how much energy? All right. Well, if we're thinking about the fact that it is gravitational potential energy that's changing, so if we do the change in gravitational potential energy would be equal to mg delta H, right? This is very similar to what we used up here, but this time we're looking at the change. We know the mass isn't changing, the gravitational acceleration isn't reasonably changing, and so therefore it must be the change in height that's causing the change in potential energy. But this question isn't just asking for the change in height, the change in energy, it's asking for the change in energy per time. So if I rewrite this as the change in energy, potential energy, over time, well, if I divide the left side by time, I need to divide the right side by time as well. All right? Now, if you look at this right here, I now have a distance over time, the change in height over time. Well, we know what the change in height over time is. It's this. That velocity right there, that 50 meters per second, is how the height is changing in time. It's changing 50 meters every second. That's the velocity as they go down. So therefore, if I calculate this number, then I will have this number. And so I'm going to go the change in energy over time is equal to mg h over t is v, right? And so there we go. We'll put in the mass, which is 75. We'll put in g, which is gravity, that's 9.8. And then we'll put in the v, which is 50. All right? And so from there, we should be able to go 75 times 9.8 times 50, and we get 36,750 joules per second. All right, now there actually is another way to do this. If you look in your formula packet, there's actually another equation that looks like this. It says P equals FV, right? So if you have a constant velocity and a constant force, then it will require this much power to be lost, right? Because if I am exerting a force, I shouldn't have a constant velocity. I should have a changing velocity, right? F equals ma. A changing force should cause acceleration. So if it's not, then there must be some other way that we are losing energy so that this force doesn't go into accelerating that v. So therefore, if I have a constant force, if I have a constant v, then that will allow me to calculate the power, the amount of energy that's being lost per second in order to allow me to maintain this constant velocity. All right? So therefore, I could have done that as well. Now, what force am I looking at? Well, if you think about a person falling, the person falling has two forces acting on them. They have the force of gravity, and then they have the air resistance, the force of the air. Now, those two, if I have a constant velocity, those two have to be equal. So what is causing me to lose energy? Well, it's this one right here, right? The air resistance is the thing making it so normally gravity would just change it from potential to kinetic. But that's not happening here. Why? Because of my air resistance, because of the force of the air. So that would be the force that I would use there, which just happens to be equal to the force of gravity. And the force of gravity, of course, is mg. And you'll notice that if I do that, I have mgv, which is the same thing that we came up with here. So there's a couple of different ways to think about this, to conceptualize how we're solving this question. But in my mind, understanding this is an important principle. Just being able to pull out an equation, only if you really understand what's going on there should you use this. Recognize that this is the force causing the loss in energy. That's important there. Okay? Let's move on to question 4. All right? So question number 4. A block starting at rest slides down the slope as shown. Okay, so that's this picture over here. So we got a 4 kilogram block. It's going down the ramp. You can see that at the end of the ramp, it has a speed of 5 meters per second, that it traveled a distance of 5 meters, and that the height, the change in height, was 3 meters. All right, so we got all that information from our drawing here. The question is to calculate the amount of work done against friction and the size of the friction force. Okay, so work, that's energy, right? That's energy. So let's start with that. Let's see if we can find the work done against friction. How much energy is going on there, right? So let's look at, if we start our 4 kilograms up at 3 meters and it goes down to 0, what should the change in energy be, right? Well, up at that 3 meters, it should have potential energy. So that would be my initial potential energy. Okay, so I'm just going to go mgh. So the mass is 4, the g is 9.8, and the height is 3. All right, so that would be 4 times 3 times 9.8, which is 117.6. So that's how much energy it starts with at the top of the ramp, right? So therefore, when it gets to the bottom of the ramp, it should still have that much energy. So this is actually my kinetic energy final as well. That's how much it should have. But does it? That's the question. Well, if there's friction, the answer should be no, it doesn't have that much energy. So let's find out how much energy it actually does have. So the kinetic energy final is 1/2 mv squared. So 1/2 times the mass, which is 4, times the final v, which it gave me was 5 meters per second. So let's calculate that. So we'll go 0.5 times 4 times 5 squared. And when I calculate that, I get an even 50 joules. Okay? So it now has 50 joules. So what happened there? Well, what happened there was friction. So how much work did the friction do? Well, the friction did 117.6 minus 50. So I'm going to go 117.6 minus my previous answer, which was 50. And I should get that friction So this is the change in energy due to friction would be 67.6 joules. All right. So that's the amount of work friction did. All right. Now, if you wanted to look at the amount of work done by gravity, you could do that as well, right? You could say the work done by gravity equals force times distance. Gravity is exerting a force of mg, which would be 4 times 9.8, and the distance would be 3. And so 12 times 9.8, which I already know is 117.6 joules. So we could say that gravity did that much work. All right. So we got some different ideas here. We know that friction did that much work. Gravity, if we wanted to view that as an outside force, would have done this much. Okay. Now, the other question here is, what is the size of the friction force? Well, we know how much energy friction took out. That's the work done by friction. We know that work equals force times displacement. Sometimes we use an S there. Okay, so this will be the force of friction. This will be the parallel distance to the force of friction. So friction is working backwards up the ramp, so it's working parallel to the ramp. So the distance we want this time is the distance parallel to the ramp. So we're going to say friction did 67.6 joules of work. It caused that much work to be done. That's the change in energy. Equals the force of friction times the distance, which was 5 meters. And so if we take that 67.6 and we divide it by 5, we get that the force of friction is equal to 13.52. If I wanted to put that in terms of significant figures, I would need to recognize that the most significant figures I have here is 1. And so I would write this in 1 significant figure, which would actually be 10 newtons. Okay. For now, I think that's close enough. You get the idea. You understand what we're trying to get to there. All right. So that's the end of our video here. We got through a couple of those questions. I hope that was helpful. And we'll go through another couple of questions in the next video.